Fantastic. Thank you very much, everybody who's joining. This is episode 74, and today we are going to be discussing eBPF tail calls with Liz.
Hi.
Hi. So for those who've joined for the first time, my name is Dan Finneran. I'm part of iSurveillance, part of the advocacy and community team.
And I am Liz Rice. It's very strange for me today. I'm, Dan's hosting and I'm a guest, and this is, it's the tables have turned.
I'm trying to take some of the load, make it a bit easy for you, make your life just that little bit easier.
I appreciate it. Yeah, it's very good. Yeah.
Fantastic. Cool. So a couple of things before we kind of kick off this episode. First thing, really, we're going to be just doing a quick overview of some of the upcoming events. Welcome, everybody, to 2023. CFPs will be coming your way for a myriad of events in the cloud native space. So get ready for all of those. But three of the upcoming events that we feel are important and are going to be happening in the next kind of couple of months. The first one being Cloud Native Security Con, which is based in Seattle. So that will be taking place on the 1st and 2nd of February.
I'll be there.
Fantastic. So
I'm actually one of the program chairs for that one. So myself and Emily Fox and Brandon Lum, who if people have been involved in the security space in the CNCF, they will know those names. So it's been really great putting together this security focused conference with
Fantastic.
them. Should be good.
Will that be a hybrid event? Will there be live streams from that?
I believe it's being streamed as well. Yeah, I'm pretty sure I've seen that's the case. Yeah.
Fantastic. And I suppose for people who kind of, I guess, maybe unaware of the sorts of kind of content that's going to be discussed, kind of what kind of the key things that are going to be kind of covered, I guess, from a...
Oh, that's a good question. Yeah, so it's very much security focused, and while we want to really concentrate on security as it applies to cloud native deployments, that does have a fairly broad scope. There's tracks that cover things like security education, there's 101 tracks, there's supply chain security. It's been such a big topic, so there's lots of talks about that. Personally, I also want to make sure that we don't, as we talk about supply chain all the time, forget about things like runtime. I think we'll be covering a whole, hopefully the whole life cycle of security as it applies to cloud native. And we're going to have some workshops as well, so that'll be fun.
Excellent. Yeah, fantastic. It's good to see that we're approaching security like from the top to bottom perspective at this point. Just as opposed to just kind of scanning at the end, we're starting to implement kind of security measures and the thought process all the way from the beginning of writing code to deploying it to actually running it in production. And
yeah. I think when we think about things like education, a really important thing is, developers being aware of things like, buffer overruns, writing things in a secure, reasonably secure way, because the way that attackers find out about vulnerabilities quite often is inspecting code and looking for problems that are visible in the source code. So the more that developers can learn about coding security, the better, the more secure we'll all be.
Fantastic. Next on our list is the State of Open Con. This is going to be in London on February the 7th and 8th. I believe tickets are still available for that. And this is a conference all really about kind of open source. There's going to be a lot of different tracks in terms of open source from a kind of almost a legalese perspective, consuming open source, what does it actually look like? I believe there's going to be some sort of user stories in terms of kind of people creating open source, how kind of their journey and how things have impacted them, and everything in terms of consuming to creating to kind of everything all around that. And then finally, at the exact same dates is Civo Navigate, again February 7th and 8th, and this is going to be in Florida. So congratulations everybody who's getting to pop to Florida. Hopefully the weather should be quite nice for that.
You're saying that would be better than London? I mean, what's to beat London in January? February, sorry. February, even better.
Yeah, absolutely. Lucky people. Excellent. So the next kind of section that we've kind of got, and what I've kind of quickly done earlier today and yesterday, was to save everybody a bit of work, but to have a kind of a look at some of the predictions that have been kind of put forward for 2023 in terms of kind of things in the cloud native space. If people do have anything that they have predictions, then please put those in the chat. But first one that I've seen kind of quite a lot really is going to be more Kubernetes at the edge. I think that's largely being kind of driven by telcos and kind of these small workloads where people are kind of running things in localized area, doing that sort of localized processing and sending things back. So, and we're seeing a lot more work in things like the special interest groups around edge computing. We're seeing a number of new projects, all focused kind of around the edge space.
I was speaking with a friend who works in this space over Christmas, and he was saying about just the scale of the different industries that get involved with edge. The use of compute in factories or on ships or in oil rigs or all these different environments. I think it's mind blowing, really, how many places we could be running Kubernetes at the edge.
Yeah, absolutely. Especially with kind of the more IoT devices and things like that as well. I've heard stories of kind of these small IoT devices along railway lines that continuously are running these edge workloads that monitor the state of the rails. So buckling and cold and all of that sort of stuff is all relayed back and sent back to these clusters and then sent back for processing and all of that sort of stuff. So there's a lot of kind of use cases that people haven't thought of that we're starting to see more of, which is it's pretty exciting, I think.
Yeah, very cool.
So the next one really, I've last year there was a lot of people talking about platform engineering. I'm still kind of learning a lot about what platform engineering kind of is. I'm still, it seems quite a marketing perspective to a lot of it. They're moving from DevOps to platform engineering, but it's I saw that it's now on the Gartner hype cycle and things like that. So clearly, it's now a buzzword, an authorized enterprise buzzword. So yeah, I mean, do you have any thoughts on the kind of push towards platform?
Well, funnily enough, you mentioned the State of Open conference, and I'm actually going to be hosting the platform engineering track. So hopefully I will know a lot more about platform engineering kind of this time next month. It's certainly, I think, an evolution of what we've been talking about when we've talked about DevOps over the past few years. My sense is that it's something, it's come to do with the organizations inside large, or the team organization inside large enterprises, where they're going to have development teams and then they're going to have a platform team, and the platform team are doing platform engineering. I think that's this sort of idea that the developers going to also look after, developers are not going to also look after the infrastructure on which they run all the code. Mm-hmm. And I guess that's my understanding of where this term has come from.
So the independent developer platform, I think, was something I saw banded around quite a lot, which is, I guess, the capability to spin up these platforms that exist in a way that makes sense for the developers and generally make developers' lives a little bit easier. Because I think, to a certain degree, we've made it kind of quite hard for developers today. Day one, it's not, here's your laptop, start writing code. It's almost, here's your laptop, install Minikube, do this, do that, learn about Kubernetes, learn about cloud native networking, blah, 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 blah. It's almost a week before you can almost write your first line of code to a certain degree. So lowering that barrier to entry, I think, is probably going to make developers' lives a little bit easier. There's a couple more that we kind of have. So I guess tighter controls on cloud spending. this is kind of a bit of an obvious one given the current economic climates, but
Yeah.
we've certainly seen companies like Cube Cost. I believe that's either a project or a company. I can't remember off the top of my head. They're now part of the CNCF. I believe they're standardizing now on metrics around pricing and cost monitoring and things like that. So I think as these specifications mature and things like that, there's going to be a lot more control that people have over what their clusters are actually doing and the capabilities of rolling some of the scale of things down to kind of save on cost.
I hope some of that will also relate to spending on energy or use of energy from a green perspective. I mean, I think a lot of the time the energy usage or carbon cost and financial cost are going to have a pretty clear correlation, but it seems like there's more and more enthusiasm around, green software engineering, and hopefully all these things will line up.
Yeah, absolutely. Okay, cool. WASM. So especially the last 6 months or so, with Docker announcing that WASM, I think some changes in Containerd and some of the underlying parts of that now, typically allowing you to kind of create and run kind of your WASM compiled applications directly in Docker. A lot more kind of new projects. Hachyderm, which is I think is a pretty new startup in that space, is all around WebAssembly tooling and getting your applications all compiled. There's also a bit of an interesting article around whether WASM will replace Kubernetes completely. I think that was on the new stack recently. So there's definitely a lot of talk around WASM. Obviously, a lot of hype at the moment, and it'll be good to see how that kind of matures and how it finds its space moving forward.
Yeah, definitely. I think if I wasn't interested in eBPF, I'd probably be looking at WASM. So yeah, it's certainly very interesting technology. Yeah.
And service mesh, there has now been a lot of new talk around service mesh. It's an interesting topic. I do remember KubeCon in 2017, where I think at least 98% of the sessions were largely all around service mesh. Everybody was demoing Istio and doing all the clever networking paths and kind of changing what traffic was doing and things like that. I think kind of the problem, it almost felt like it was too soon, and people kind of was like, this is amazing, but we don't really know what to do with it. And it had quite a heavy footprint. There was all the sidecar containers and things like that. So I think there's been a lot of work revisiting service mesh. There's been a lot of work making it more efficient. There's been a lot more work in terms of listening to what people are actually wanting to do with their networks and things like that, and what they want to see and how they want to manage traffic. So I'm super excited to see, kind of service mesh 2.0. Is that even the right term? Because it almost feels like, things are changing a little bit there as well.
Yeah, for sure. I mean, Cilium service mesh, I think, when we first announced that kind of end of 2021, it set people thinking about what's possible, with sidecarless service mesh. And, we've now started having people using the Cilium user survey showed there are people now using Cilium service mesh ingress in production. So, it works. There's still some of the pieces like the encrypted communication between workloads, but that's on its way. So it's going to be exciting to see how that speeds things up. Really, I think the performance is going to be really, really good to see the sort of measurements on that.
Yeah, and I think from the playing, I guess playing is the best way I can really describe it. The usage that I've had kind of with Cilium mesh and some of it, it's been a much more streamlined experience than it was 5-6 years ago now that service mesh kind of first appeared. It's much more kind of transparent and getting it actually up and running. You're effectively just asking the cluster to do things with networking, and it will just go ahead and do that. It's a much nicer experience than it was back then.
Yeah, and as it should be. And from a developer's perspective, developers shouldn't have to think about how their services are communicating with each other. Maybe they should be thinking about which services want to talk to which other services. But I think the rest is underlying detail that maybe should be left to the platform team, platform engineering.
Absolutely. And finally, the continued success of eBPF. It's been I've not been at ISO too long, but I've basically spent the last 4 months or so, I think, getting my head around eBPF and getting a better understanding of it. I'm really super excited to see kind of more usage around networking, more usage around security, and this kind of is going to lead quite nicely onto what Liz is going to be talking about later today, which is helping people gain a better understanding of how eBPF works and things like that.
Yeah, looks like we've got some pretty good comments and points being made in the chat. So first of all, hi to everyone who's watching. Good to see you, and happy New Year, everyone. So I see Zaran talking about when we were talking about the cloud spending, the price of cloud resources are way overinflated, and the pricing model is deliberately complicated too. I think that's
topical. Well, it is one of those things. Unfortunately, with cloud providers, you don't necessarily fully understand exactly what's kind of happening under the covers. So it's sometimes a little bit hard to justify prices to just a VM, but you're also getting IPv4 addresses on the networking, and there's underlying various other things that you not necessarily know that you're paying for. But things do get quite complicated as your architectures expand and things like that.
Yeah. Martin Casado, who's he sits on the ISO board, and he's an investor at Andreessen Horowitz, and he did an article at some point last year talking about the kind of cost of, like, at what point does it become more effective to run your own data center rather than using the public cloud, that's really what the balance point is. Can you do it yourself cheaper or not? So and I think with things like the cost of energy changing, that could be changing the cost of operating a data center, I would imagine, quite significantly.
Yeah, absolutely. I mean, with VMs in the cloud, there's no ops teams that you need to employ. There's no, there's a lot of things that you not necessarily have to worry about so much.
Yeah.
I do like, there's a comment here from Bojanche. I hope I pronounced that correctly. Anything will replace anything anytime soon. Smiley face. I can't argue with that. Having been through FreeBSD jails and Solaris zones on projects many moons ago, it's good to see kind of things going round in circles. Will mainframes come back though? That remains to be seen, I suppose. We shall see.
Yeah. Things always come around, like thin client, fat client, thin client, fat client. And looks like we're getting some good debate here as well about the cost of I've not come across Hetzner, but Bojanche has mentioned Hetzner, which is something I haven't.
They are a cloud provider, and the only reason I know this, I believe, is because I saw a cluster API provider for Hetzner appeared recently. Cool. Well, we can revisit some of these. So if people, please keep your comments coming, and we're going to move things over and hand things over to Liz.
All right. So I've been writing a book. I've been working on this book called Learning eBPF. And as part of that, I have written lots of different kind of code examples and tried to illustrate various things about eBPF and how it works. So I'm a big believer that talking about things in a hand-wavy sense is okay up to a point, but eventually I need to see the code so I can understand what's going on. And one of the demos that I wrote is about tail calls, and I thought maybe that would be an interesting topic for an eCHO episode. So I guess I should probably just start by talking about like what tail calls are, because they're not exclusively, by no means are they exclusively an eBPF concept. They're a general programming concept. So you know how if you have a recursive function, and well, even before we talk about recursion, just when one function calls another function, that puts a frame onto the stack. So every time you call another function, you're putting a frame onto the stack, and when you return from the function, it sort of unwinds and the stack can shrink again. And if you have a recursive function where you have a function that calls itself over and over again, however many times, depending on the depth of that recursion, you can end up with a big stack, a large number of function calls. You've got a lot of frames on the stack. So the idea of tail call optimization is to say, well, if you were to call the recursive function right at the end of the function, so if it were to call itself as the last thing it does, then the stack frame is not really holding any useful state, because all you were going to do when you return to that stack frame is just jump back up to the next stack frame. So the idea of tail call optimization is to say we can just not bother storing these stack frames. You can kind of replace one function with the, we only need the current function state. And that's the same principle in eBPF tail calls. eBPF tail calls have been supported for really quite a long time. I think it's 4.16 or something, like really quite an early kernel. And it was a pretty key way of decomposing BPF programs. Before, tail calls have been supported before BPF to BPF function calls, if that makes any sense. So if I can, I don't think I can do this myself, but Dan, if you can bring my screen onto the, brilliant, all right. So I'm gonna just try and write a little example of a BPF program. I'm going to use BCC, which is Python. This is really, I just like to use it because it's much quicker to kind of create a program in BCC than it is in some of the other frameworks. So it's more for demo purposes than anything else. So here is my Python program, and within it, I'm going to write a C program and store it in a string. And I'm going to start by just doing a very sort of basic entry point, and let's call it, I'm going to attach it to a raw trace point. Probe. Sys enter. But this is one of this raw trace point probe macro is one of the things that BCC does to make my life a lot easier, because this is going to say, I know I'm going to attach to the trace point that's at the entry to every system call. And all I need to do to sort of make that happen is this tells BCC to compile my string and load it into the kernel. And before it does the compilation step, BCC goes through the program and says, are there any interesting macros I need to be aware of that I need to rewrite into proper C code? Oh, here's the trace point probe. I know that I need to attach this program to the sysenter entry point. So I don't even have to attach it myself. I will, when I generate some print, I want to print it out. So do that before I forget. So I'm just going to start by putting in a trace line so that we can see something happening. So this is just going to be triggered every time there is a system call on my machine, which should be like all the time. And I think that should be sufficient to generate lots of trace. There we go. Lots and lots of syscalls being triggered on my machine. Something else I'm going to do is just show you with BPF tool. Actually, I'll bring this up the screen. So since I've terminated that program is no longer loaded. And there are a few eBPF programs running in my kernel. They've all been loaded by systemd. So all of these ones that sort of 48 through to 59, we can ignore those. We're not interested in those. But if I run my program and do the same thing, this is a terminal on the same virtual machine. So you can see that the ones that are 48 through to 59, whatever, are still there. But here's the program that I've just created. So it's called sysenter. It's a raw trace point. It's associated with this tail.py program that's running. Okay. So haven't done any tail calls yet. Haven't done any function calls at all yet either. Now, suppose I wanted to, this is a kind of bit of a toy example, but suppose I wanted to, well, then let's start by saying, let's look at the opcode for each individual syscall. And I happen to know, in fact, I'll show you the documentation for raw trace point probes. This is from the BCC docs. And the argument is a pointer to a struct, which is the trace point args that contains all the parameters of this trace point. And if I look at the trace point for sysenter, which I have here, so here's sysenter. arg0 is the state of the registers, and arg1 is the ID. This is the identity of the system call, or the opcode for the system call. So I can get hold of that opcode. CTX is the parameter that's been passed in, which is kind of hidden by that macro, and I want argument 1. So that's going to be that ID. So hopefully now, if I run this, we'll start seeing the, not that one, not that window, the other window. Stop that, run it again. And now we're seeing the ID, the opcode for each different syscall. And let's say that I want to do something different for different system calls. I could have like a big switch statement here that goes case. Let's say I want to ignore, I need to switch on something, switch on the opcode. And if it was 64, maybe I want to do something different. Perhaps I want to ignore this this opcode. So let's create a function that does that. And for everything else, I'm going to do, oops. So I could structure my code to look very much like this, with just like regular function calls. And I would need my ignore, what did I call it? Ignore syscall. Okay. So now that should actually work. So let's try it. I think it should work. Tell me if you think it shouldn't work.
I think the function names don't match.
Oh, that's well spotted. All right. Okay. So can't really tell, but we can't see any 64 being traced out. Let's just check that that's true. Okay, so we see 64 in the timestamp value here, but we're not seeing it as an opcode. So I think that's working. Now, this works for this does work. But suppose we wanted to do something really, if we wanted to do lots of complex processing here, if this was something more complicated than just tracing out system calls, we can, and suppose that we wanted to decompose our tracing into lots and lots of things. There's only a 512 byte stack in eBPF. So if I wanted to call from here to something else, to something else, to something else, I could rapidly exhaust the stack. So instead of calling my function directly like this, I can use a tail call. And doing that, or to do that, I set up a map. So an eBPF map is a data structure. They're all kind of key value pairs of one type or another. And there is a type called a BPF map type program array, which BCC shortens to BPF prog array. I'm going to call it syscall, and I'm going to say there's about 300 system calls, so that should be big enough. And instead of this whole switch statement, delete, I could do syscall call. I'm going to pass in the context, and then I want to call a function that's identified by the opcode. I still need the return function, and I deleted my trace statement. Now, I'm going to leave something in here that traces out if we get to this point in the code, and that's going to be important. So now, at the moment, there is, I can leave that there for now, I think. So at the moment, there are no entries in my program array. So it should always call, or it should always generate this line of trace for every system call. Let's see if that works. Oh, I've still got the grep in there. I think I've managed to colorize. Hope that's still visible. I guess I managed to quit it while it was printing out in red. That's exciting. Yeah, so that is tracing out every single type of syscall because I don't have any alternative. Now, when we call a tail call, we are never going to return to the calling function. So if I successfully manage to call a tail call here, this will not get called. We'll never hit that line. But it's there as a kind of fallback. So if there isn't a program that we want to, that matches our opcode in this case, then we just fall through to executing the rest of the function, which is kind of handy. So what I need to do is create an entry in my program array that's going to call ignore syscall. Let's say we're going to do this for that 64 that we keep seeing all over the place in here. And I have to set this up in BCC. Well, no, I have to set this up in user space. And I have to do a couple of things to do that. The first is I need to load the function. So I'm going to call it ignore function. Oops. Ignore, what did I call it? Ignore syscall? Now, I have to say that this is going to be a BPF program of type raw tracepoint. Every tail call has to be the same type of BPF program as its parent. I'm going to get hold of this program array. So that is the map, the program array. And I'm going to create an entry for, I have to use C types to, unfortunately, let's say 64. The entry for this is going to be the file descriptor associated with this ignore function. So we've got one entry populated in this map. So there are 300 slots for system call, and only one of them is populated. That's the entry for system call 64. And I'm saying we want to call this ignore function, and it will. The one other thing I need to do is take out static. And I think this should work. Okay. I'm not liking that because I can see 64 in there. Did I save it? I did save it. Is it called ignore syscall? I think it is. Because what I'm worried about here is I saw 64 and we're saying that it shouldn't call through to 64.
Is the table called opcall, not syscall?
Table is called syscall. The function is called ignore syscall, which I have loaded, and it's BPF. The table. This is what I've done wrong. This should be get table. I wonder what I did by just doing. No, that still looks the same, doesn't it? You know what I'm going to do? I'm going to just put in a different trace here just so we can see. This is what we like to do, a bit of debugging live on the internet on a Friday afternoon. I'm not seeing ignore there at all. It's going to be frustrating because if I have to, I'll bring up my other example. Here's one I prepared earlier version. But it might not be liking this. I'm not sure, but don't think it should matter the order that it's. No. The one other thing I've done differently in my example is that this appears later. I don't think that should matter. But... one other thing I can do is I could have a look at the set of programs that have been loaded into the kernel if I was root. Okay, this is interesting. It's only loaded sysenter, whereas if I've successfully created a tail call program, I'm expecting to see ignore syscall also as a version here. If anybody online has figured out what I've done wrong, then please feel free to let me know. Okay, so got a raw trace point. That looks right. That looks right. That looks right. And that looks right. Oh, I know what I've done. I am an idiot. This needs to happen after because this is blocking. All right. So basically, I was never creating my entry in the program. Right, now we can see it. So we can see the ignore function being hit. I could take that trace out again. So we should never see that. All right, so if I look for opcode 64, we'll still see 64s in the timestamps, but we won't see them listed as a system call. And let's look at the programs loaded into the kernel again. And this time we can see not only do we have sysenter, but we also have this ignore syscall function. So the tail call is another BPF program. I could invoke that independently and directly if I wanted to. Yeah, so that's that solved that problem. Good. Because tail calls have been supported since a really quite, in eBPF terms, quite an old kernel, you could use tail calls on some much older systems. You can now also call from BPF programs to other BPF programs. It's called BPF to BPF. Looks like function calls. But I can't show you that in this demo very easily because BCC doesn't support it. So it supports kind of compiling static functions, but it doesn't support the BPF to BPF functions. And I believe that that's just to do with BCC not knowing how to interpret the function calls or not knowing how to pass that correctly to the kernel loader. But yeah, it's kind of I don't know. I think it's kind of cool that you can do this. You can do the tail calls in BCC at least. The other thing I really like about it is the fact that if you don't have an entry in the program array, you just drop through and carry on executing as normal. It doesn't throw an error or anything. So that's kind of neat.
This is my first time seeing like I guess almost C encapsulated in Python. Presumably it's building the eBPF object and then loading it at runtime.
Yeah, that's another thing that BCC does and makes my life easy. Again, really great for demo purposes. That under the covers, BCC is invoking Clang to do the compilation. Before it does that, it's doing this kind of pre-processing pass to turn things like the macros into real. I mean, there's a sort of hash defined pass like normal C code, but it's also doing things like dealing with this. So this is not regular C, right? You can't normally call a method on an object in regular C, but BCC, based on, I've defined this program array up here, knows that this is that the underlying C is going to be, I think it's BPF tail call, maybe something like that. And I'm going to get the parameters probably in the wrong order, but it's probably something like CTX, syscall, opcode, something like that. And BCC just kind of makes that a little bit easier to write and potentially easier to read.
Yeah, it's quite nice that it abstracts away and it makes the code easy to read without you having to fully expand it all into what's happening under the covers to a certain degree.
Yeah, there are other things. I mean, things like these macros, and there are similar macros like this in libbpf as well, where on the one hand, this makes things so much easier. I didn't have to worry about what the parameters are to a trace point. I didn't have to attach down here. Normally you would explicitly have to attach your program to some kind of event. The downside, I would say, is I've referred to this CTX parameter a couple of times, and that's hidden within that macro.
Yeah, kind of looking away and then looking back, it's just all of a sudden something's randomly being referenced, which is kind of a bit confusing, I suppose.
Yeah, I see some interesting questions come up as well. So
there's a lot of questions. I will pop some of them up if that's okay.
Yeah.
So yeah, this is a good point. There's a secondary question to this, but the idea of writing C again after 10 years took me by surprise. Yes, to a certain degree.
We were chatting before we went live today that this sort of about our pasts with like C and Python and so on, and I spent a lot of my early career writing C code and, struggling with setting up your build tool chain and everything. It's always a bit of a nightmare. And from that, compared to that, things like Python, it's so easy, and it's true. You can just import anti-gravity, and it's, things are just made and done magically for you. And then I went from that to Go, and going back to a compiled language, because with Python, as you could see with me, hacking away there, because there's no compilation step, I certainly just tend to fall into this kind of hacky mode where you just keep trying things until it works. Whereas with a compiled language, you've got that much greater sense of, once I get it to compile, I'm pretty confident it will do what I want it to.
Yeah, absolutely.
Yeah.
It's a good question. I believe it has been partially answered, but we'll just kind of bring it up as well. Something more friendly that can compile to eBPF than a C program.
Yeah, so I suppose BCC is a bit like, or BCC's version of C is a bit like a kind of combination of C and Python code. Whether you consider that more or less friendly, I don't know. You can now write your eBPF code in Rust. Again, whether you consider that more or less friendly, I think it's so the Rust compiler supports BPF bytecode as a target, which is key. I think if I were writing, not just demo, but if I was writing for real, I would write in C and use libbpf, which has all this compile once, run everywhere support. So as we were just talking about, the BCC is going to do the whole compilation step here, which means you've got to have the whole build tool chain. You've got to have the compiler on that machine, and you've got to wait for that compilation step to happen. So this is super good, super easy for writing demos or getting things running really quickly as an individual. But I think if you're trying to ship code, ship real, applications to end users, I probably wouldn't choose this. I would probably want to have a compiled option. And then there's not just the eBPF program to consider, but there's also the user space part, the part that does stuff like setting up your maps in user space and loading the eBPF program into the kernel. And then there's a ton of different options for that. Things like, Cilium uses the Cilium eBPF library, which is Go. So for those of us who like Go, that's a good option.
Absolutely. And it's that eBPF programs have to be quite small. They have to meet stringent requirements to actually be loaded into the kernel. And I suppose it's these requirements which really, you can't write an eBPF program in Go and have that loaded into the kernel.
Yeah.
Go has a garbage collector. It has a lot of wrappings around the code which make it safe to run and things like that. But
multiple threads as well. You can only have one thread in a eBPF program.
So the requirements of the kernel force whether a programming language can create something that will actually run there or not.
And the compiler also has to support quite a lot of attributes. This is something that I've learned a lot more about through the course of writing my book, the extent to which the compilers had to be changed to understand not just how to generate the bytecode. You've got to go from source code not to regular machine code instructions, but to bytecode. But also things like some of the attributes that people use, particularly for the things like compile once, run everywhere. That's required some extensions that use these attributes that basically say whether or not you're whether you want to generate BTF information, which describes the data structure describes the format of a data structure. So it's so interesting how eBPF is not just the kernel, it's the kernel and the library that you're going to write your code in and the compiler support and the user space ability to load the program into the kernel using BPF system calls and all the rest of it. So there's a lot of different components that had to come together to make eBPF as a system work.
Fantastic. Yeah, it's there's a learning curve to writing, eBPF code. There are certain functions that you may normally use in C that you can't because they're unsafe. The code has to fit into the eBPF box in order for it to run at the end of the day. And almost tail calls are a way of fixing some of the limitations to a certain degree of eBPF programs. There was a question in terms of the limit of tail calls that somebody asked, which was, the instruction limit has gone effectively.
Oh, yes. Yeah. So the instruction limit today is 1 million calls, although it's not really a million instructions. Although it's not really, there are 1 million instructions in the program. The verifier will look at 1 million instructions before it kind of goes, no, sorry, I'm done. So you might be hitting the same instruction multiple times in that verification process. So it's more of a complexity limit than a instruction limit. But yeah, if you can call BPF to BPF calls, either BPF to BPF that looks more like a regular function call, or tail calls, yeah, the instruction limit is more or less, I wouldn't say that it means there's absolutely no limits on the complexity, because you've still got this quite small stack that you have to fit into. But yeah, it's much, much, much more relaxed than it was, earlier kernel versions.
Fantastic. I can't help but notice that Quentin is doing a fantastic job of answering questions at a rate of knots as they're occurring. So this is fantastic to see. So we've mentioned how many tail calls you can typically call there, how big programs can actually get. What else do we have here?
There's an interesting point here. Quentin's pointed out that there is a limit of 33 tail calls. Actually, I saw this little bit of history. I think the limit was intended to be 32 tail calls, but there was, one of the two problems in software engineering, naming, and I can't remember what the second one is, and the third one is out by 1 error. So yeah. And it has been fixed up now to be consistent, but that's how we ended up with 33.
Excellent.
And yeah, Quentin also made the point that about loops. So you used not to be able to have a loop in the bytecode. So compilers you could do what's called unrolling. So if you had a for loop or something, you tell the compiler to unroll it, and it just emits the same instructions over and over again, however many times for the loop. But now there's also some helper functions that allow you to effectively loop through, loop a certain number of times over a function, or iterate over a map. So yeah, I think things are getting easier and easier for newer and newer kernel versions and compiler versions.
Fantastic. Excellent. We've got a couple of minutes left. I think Quentin's pretty much answered largely everything. A quick shout out from Nuno there, quickly passing by to wish everybody a Happy New Year. And let it be the year of eBPF.
He has been doing on Twitter, I've been seeing he's been doing all sorts of interesting things, running eBPF and Cilium on WSL. So which is not an environment I'm super familiar with, but I was pretty, it's impressive to see that you can run Cilium in that environment.
Yeah, absolutely. That's interesting. I mean, that's all running in the Linux VM that's part of WSL, I guess, or whatever it actually is under the covers.
Yeah, I think the first version of WSL was like a syscall kind of emulator. But I've got a feeling it's something different now, and I can't remember what.
So they kind of did reverse wine, I suppose, which is a Windows syscall catcher for Linux, and they did it the other way around.
Okay.
Excellent. Fantastic. Well, thank you, everybody, for joining today's live stream. Before we go, one additional thing that we forgot to mention was the iSurveillance badges that were announced just towards the end of last year. It's been fantastic to see so many people taking part of the courses and earning all of those badges around Cilium and things like that. So if anybody has any feedback and things like that, we'd love to hear more in terms of what badges people want to earn and things like that. So we're really excited to see how that grows. Cool.
Absolutely. We'll add a link to the labs that have badges in the show notes.
Fantastic.
There's also, actually, while I mention the show notes, there's a link in the show notes to not just the preview version of my book, which doesn't yet have the information about tail calls, so you have to wait for the published version. There's also a link to my GitHub repo, and that has got a tail call example that's very similar to what I showed you today.
Fantastic. Well, thank you very much, everybody, for joining us on this Friday afternoon, morning, evening, night, wherever you may be located. And we look forward to seeing you all again next time.
Bye.
With that, thank you very much. Bye.